much. So thank you also for the invitation here. It was nice. So I'm not a multiscale, fully multiscale people. This is part of my interest. So this is a work of some years ago with a colleague from Chile. It's motivated by a very specific application. So you will see this motivation is very clear. The talk is in the direction of the application. So the application is the so-called magnetic resonance elastography. This is a medical imaging technique. It's called tissue imaging. So it means it's used by doctors to understand the tissue of patients without entering into the patient. So it's like when you go to the doctor and try to touch you on the skin and see if there is some problem. This is more or less the advanced way of palpation that they use. And it works in this way. So there is this is a patient. There is a mechanical vibration put on the patient, and then the tissue moves. Then they record the image by MRI. So this is a relatively low frequency. So it's not ultrasound. It's just mechanical vibration. So they record image by MRI, and then for each small voxel space, they have a displacement field. So this is what they can manage to obtain. And then from this displacement, they can invert somehow the results and estimate tissue properties in terms of elasticity properties, so Young modulus or compressibility and so on. So this is used, widely used to assess if there are diseases such as cancer. So this is an image for just example. So you can see there are different colors means different stiffness, for example. And it's known that the cancer is stiffer than normal tissue, so you can see if there is some problem. So then the question that motivates this work is a discussion with some group of people working on elastography. They would like to understand if it's possible using this technique to estimate assuming it's the fluid inside the tissue, if you can estimate something about the pressure of the fluid. So this is about the background. So they have a very simplified experimental setup. So they took a gel with some air bubbles inside. So this is the MRI image. And they put this small cylinder in a kind of box, and they move the box, and they do the experiment for this phantom. And they try to understand if they compress the phantom before moving it, so if they can reconstruct this change in pressure. So this was somehow the setup of our work. Okay, there are also other applications. So my colleague is from Chile, and in Chile it's very common to have earthquakes, so they have also a lot of seismic data. So somehow this is a similar, mathematical framework, physically not so similar, but we also have waves exciting the domain. You want to understand if there is something in the macrostructure you cannot see from outside. So they have, for example, in this case, boundary data, and they would like to understand if there is, for example, somewhere high porosity inside the soil. So motivations, once more, so we want to estimate some physical parameters of a tissue or a material. And we don't want to do the full-scale model because this is, as you can imagine, it's difficult from the computational point of view. Because you need, if you want to resolve small inclusions, you need a high resolution. And if you want to estimate something, you need to iterate this for many times, so it's costly. And the other reason is that in all these applications, you don't have the resolution in the data. So these images I show are very coarse. It's like millimeter size, so you cannot. So there is no chance that you can parameterize your model at the microscale. You have to do something which is effective. So the goal is to construct an effective model. We use two-scale periodic homogenization. Okay, so I will just go through the steps. First, the forward problem. So we apply two-scale homogenization for this tissue with small inclusions. Then I will show how do we manage to find the solution of the cell problems so that we can do this more analytically. Then how do we apply this to the inverse problem? Okay, so this is now, I guess, very standard setting. We have an incompressible elastic material, which is gray with a lot of small bubbles. we assume that so this physical parameters, the shear modulus is given, and the pressure of the bubbles, of the air inside the bubbles is given, and we call phi the porosity of the material. So it's more or less the ratio of the gas volume over the solid volume. Okay, so we do periodic homogenization now in this talk. We have a, say, a cell. So epsilon is the size of the cell. And we assume, since we want to do this elastography approach, so experiment, we have a periodic excitement on the top, for example, which is a given frequency. So we can move everything to the frequency domain. So we just look at the harmonic of corresponding to omega. So the equation I want to solve is linear incompressible elasticity. So this is the equation in frequency space. Sigma is standard tensor, and so E is the deformation tensor, and Q is Lagrangian multiplier because we want to do incompressible material. So we have boundary condition on the external part, which is standard. So we have, for example, here we assume to have a given displacement. This can be fixed. This can be free boundary. Then we have to put the boundary condition on the small bubbles. We assume the perfect gas law, so it means assume the bubbles, so the boundary moves around the bubble. Then we have a volume change, which can be computed from the integral of the displacement around on the boundary of the bubble. And this displacement will induce a pressure change, proportional to the inverse of the volume change. So this amount, the additional pressure you get when you move the boundary by D. And this can be used to set a boundary condition on each of these small interface, which is this one. So it's so this is the force on the bubble on the material is proportional to this pressure, this integral of the displacement. So putting all together, this is the equation we want to solve as the fine scale. If you want to do this in a fine scale approach, you have to resolve the interface of each of these bubbles. So this is, it can be not only complicated because it's very a fine mesh, but also because this boundary condition is not standard. So you have to, if you define an element, you have to couple all the degrees of freedom around this together. This is not standard. I don't know if you're familiar with it, but it's not a nice thing to do because you have to use some trick to solve this. For example, we can do it by iterating solution. So say it's not nice from the finite element point of view. Okay, we did it for an example. It was in this case was I think was 1 by 1 square, and we had to use 125,000 elements more or less, and we get a solution. So this is what we got. So we are moving the thing in epsilon direction, so it's compressing here and it's expanding on the x. So we say we don't want to do this always, so we try to then homogenize the fine scale. And we use periodic homogenization, so it means we have now a slow variable which is called x, and a fast variable on the small cell which is called y, which is x over epsilon. We want to describe the effective material on this scale. So we use asymptotic expansion. We expand D and Q in series of epsilon. And we assume, of course, that so these two variables are periodic on this cell. And we have a two-scale spatial derivatives where the fast scale appears when we derive in epsilon. So it's now standard. We put this expansion in the equation, and we try to find the equation for different order in epsilon. So we have so the first thing, this constraint of divergence equal to 0 can be written in different orders. In the first order, we get that the first, so the D0 is on the leading order, so the effective displacement is incompressible. Sorry, it's it doesn't depend on the fast variable. So you can solve quickly the first. So we can quickly solve the y dependence of the leading order, and say this depends on an x. While for the other orders, you get this recurrency condition, so the divergence of decay depends on the divergence, on the slow divergence of decay minus 1. This can be also used to look at the boundary condition we have on the bubbles. So for the first order, you get the integral of d0 is 0. And then for the other orders, you get the integral depends on the divergence of the order before. Okay, so this is the equation for the order 1. I will not go into details, so you can do this exercise for different orders. You get similar equations. The important thing is that it's also standard. So if you do the equation for order 1, it will depend on the solution of order 0 and so on. Yeah. So how do we close the system? You have to use compatibility condition, which means so your integral of the volume forces in each order must be equal to the integral on the boundary of the boundary forces. So this allows you to write an effective equation in different orders. For example, for the leading order, which is the one we are interested in, we obtain this equation. So now it's only d0 appearing. So this is a compressible material. So there is no Q anymore. And the compressibility tensor is this C effective. So one see that this depends on the pressure of the inclusions on the P. Depends on the original shear of the solid matrix, and also on a term which is depending on the solution on the next order. Yeah. So this is the fine scale contribution to the compressibility. If you're familiar with this, so you can recognize, since if you put 0 pressure, you will see that it's the same results as if you have a Stokes problem with void inclusions. Okay, so the problem now we want to get rid of this fine scale contribution to have a practical computation of this tensor. And the idea is this is the average of a stress of the fine scale solution. Okay. The idea is to change the variable. So this trick was in a previous paper. So we rewrite the displacement and the Lagrangian multiplier using rotating the frame according to the deformation tensor of the 0. So this is formally it's relatively simple. If you do this, then you can write everything is linear, so you can write this sigma, just taking out the rotation. Okay. And then you can plug this in the equation above. So you can see that you can actually write this tensor. You can separate the deformation tensor from the CF, so you get an expression of a 4-order tensor where this term now doesn't depend on so it's dependent on an equation, but it's not depending on the fine scale. So it's an equation which you can solve independently given the setting. Yeah. Okay, so now this is our compressibility tensor. As I say, so these two variables, key and eta, are additional variables, and they are solution. You can show that they are solution of a set of problems, which is this form. So now there is no displacement involved. So this is completely given once the shape, so once the size of the cell is given, and once these boundary terms here are given, they depend on the physical setting you are in. Yeah. So again, mu is the shear stress, so it's the shear modulus of the material, and PA is the pressure of the bubble. Yeah. So in 3D, you have 3 different problems. So again, you say that if you compute this solution, then you can plug this here in, and then you have the effective compressibility of the material at the macro scale. So there are only 3 problems because by symmetry properties, you can show that this tensor is, so it's a 4th-order tensor, but there are several entries which are the same. So you basically have to only solve 3 problems in 2 dimensions. So this is also the standard way you fix the parameters, you solve the problem, and you have the effective material, and you can solve then the homogenized problem. So this is the example. So it works. So this was the figure I showed before of the displacement and the very fine scale computation. And this is the same if you use the homogenized approach. So we also did other comparisons, more detailed. So it's not just the ice norm; it's also numerically accurate. Okay. So the other problem is now we don't want to solve these problems for every different configuration. So we try to solve this cell problem somehow analytical or semi-analytically. The idea was the following. So we have a lot of symmetries. We just try to exploit the symmetries. So this is the 1-1 problem. So there are 1-1, 1-2, and 2-2. This is the 1-1, which is very similar to the 2-2. Because so they are not incompressible. It's like a elasticity with a fixed divergence. So the first observation is that if you have pressure non-zero, this will just shift the eta, but a constant. Okay, so we can remove the pressure and assume that we just linearize in pressure. Then we have this equation. This is linear in mu. Okay, so we can just solve this equation and take into account this linear in mu, and we are left with this equation which doesn't depend now on any physical parameter. For the 1-2 problems, we can just observe that the solution is linear in the shear modulus. Okay, so we have now these simplified steps. So I rewrite the equation here we want to solve after removing the physical constants. Okay, we need these equations to fill our fourth order tensor. Okay, so these are the terms that we need to in each coefficient. Okay, now so I want to. So the term that I need is the average of the solution over the cell. Okay, so how do I solve the problem? Let's take this 2. I sum the two problems, and I get a problem which is symmetric, so radial symmetric, because the boundary condition now is only on the radial. Okay. And since the problem is periodic, so the solution goes to 0 on the boundary, so I can approximate this cell with a circle. So now I can look for a solution which is in polar coordinates and depends on the radius. And one can find a solution in this case, which is this one written here. So you can take the solution average and get the coefficient that you need for your tensor. So approximating, so there is approximation in between, which is the one saying the cell is not square, it's round. So it will be say good if the bubble is small. It will be not so good if the bubble is big. Okay. So again, so here I don't need the solution in space. I only need the average, so I can. Okay, so I can use also tricks because I only need the integral of the solution of the cell as well. And for this problem, this is so we just use an easier approach. One can say find a limit solution if the porosity is very big, and if it's zero, we just say okay, we interpolate the coefficient with two different values of porosity. Okay, so then we get these expressions. So this is the original fourth order tensor, which is completely defined if I specify these three coefficients and they look like this. So now this one here, the last part is the one that depends on the fine scale approximation with this analytic solution. Okay, if you want to have some more details, so this is the basically, so this is this coefficient here. Analytically is the green line, and for some values of the blue. No, the blue one is the analytical one, and the green one is the computed using the child problem. So you can see that they are in very good agreement. Up to a certain porosity, then we don't care about very high porosity. So now we have our fine scale parameterized analytically in terms of P, A, mu, and phi. So we are able to solve, say, the homogenized problem without solving the cell problem. Okay, how do you use this? We use this for our inverse problem. Now again, we go back to this application setting. We want to have a material which is excited on the top with an harmonic excitation. We have available displacement field inside the material. Okay, so this is a selected points inside the material. And we want to determine the physical parameters. And we will focus now on determining the porosity of the material. So how do we do this? Is all with a variational-based approach for the inverse problem, which is also standard. We define a cost function, which is now the L2 norm of the difference between solution of a given porosity phi and our experimental data, our say measure data. So okay, so the d phi is solution to this problem where the effective tensor is depending on the given phi. To find the minimum, we have to differentiate this equation with respect to phi. Okay, so this is the say the fresh derivative. So the derivative of the problem with respect to phi. So this solution is now so this d phi d phi. The thing to notice that there is a so the density itself depends on phi, so you get an additional term on the right hand side. So we want to compute the gradient in a direction theta, so we have to compute this term. And to do this, we use a joint problem, which is defined in this way. So this is useful while we can, because we can, if we test the derivative equation with the solution of this problem, in this expression, so it will become clear when I also test then the joint problem with the derivative solution. Okay, now you get two expressions. We have the same left-hand side, okay? And here we have the term which is very similar to the one here. It's just the theta missing here, okay? So you can, since the problem is linear, you can then replace this term by this one here, and this one by this one here. Okay, so it's basically, yes, so now this term is used to compute the gradient. Okay, what's the conclusion? Now, this is the derivative in direction of theta. So if I want to decrease my functional, I have to choose theta, which is multiplied by this term. Okay, so if I solve my, yes, so if I use this say S and this theta in this way with a given alpha bigger than 0, then my gradient will be negative, so I will move toward the minimum of my functional. In practice, so you have to avoid local minimums. There are also tricks. Choose this alpha. So you can change the step size by each iteration. So there's a more heuristic approach to get better results. But so the key point is that we can solve. We need to solve just for Z, so the adjoint problem. Then we can compute this S. And the other key is that now we need for this derivative of the tensor, and then we can compute this by using the approximation, analytical approximation for C. We don't need to, otherwise we need to do this in finite difference, for example, solving for two different phi and then do a derivative. So this is the summary of the procedure. So we start with a linear, with a constant piecewise porosity. We evaluate the stress tensor, we compute the solution d phi. Then we look for the gradient, we evaluated the analytical derivative of C, then we can compute our direction, and then the new porosity. And then this alpha depends on, in our case, on the values, the functional, the different steps. So we only need to solve basically we only need to solve homogenized problems, so it is no macroscale anymore, because we can compute this term analytically. Okay, let's do some results. The first test is just concerning this approach, so we just see if this is working or not. So I assume to have a macro scale material with a different porosity, and just see how the inverse problem works. So this is the solution in this case. Again, this is a very simple test because we are just using the effective model to compute the forward and the inverse solution. So it's kind of more as a kind of validation of how robust is the approach. And then we try to do a different test. So we try to do a multiscale inverse problem. So we assume to have our data generated on the micro scale. So we take the very small mesh. We solve the full scale problem and we take the results, and then we interpolate the results on a very coarse mesh. So this is our, okay, so now the results are generated assuming a bubble distribution which is not uniform. And then we have a very coarse mesh to interpolate the results on. And now we want to try to use the effective model to see if we can reconstruct that there is a high porosity inside. So this is the results. So you see that I must say this is not periodic anymore. So the setting is not a very rigorous one. So we can expect that there will be some problem on the boundary of the material and on the boundary between different porosities. So this is the result. So we see that here is the cross section of the domain. The black one is the exact porosity. So there's larger bubbles here and smaller here. And you can see that if the noise is not too big, in a normal range, the argument finds a high porosity subdomain in the middle. So and it's the 3D figure you see as also on the boundaries there are artifacts. So this validates also the fact that the analytical approximation is good because we are using this to find the minimum. So this validates both the inverse problem solution and the analytical approximation of the tensor. Okay, you have to put the value of the functional just for information. So this is how much the cost functional reduces during iteration. One can see that if the noise is very high, then there is basically no improvement. Otherwise, it's very quickly we find a good value. By 20% less of the initial cost, then stays more or less constant. Okay, this is already conclusive remark. So we did an homogenized model of elastic material with compressible with gaseous inclusions, and we used a semi-analytical approximation for the effective model in order to solve efficiently an inverse problem for estimating the porosity. But can be used in the same way also just with other parameters. So it's not just this was just a choice because the porosity is the less trivial. This is not linear, while the other two parameters are linearly into the model. So I said this is a work of some years ago, but now in my case it's again interesting because I have other perspective. So one ongoing work is if we can use different inclusions models, so not a gas, but for a fluid or a void, and if we can also use different physics for the surrounding tissue. If you want to have not elastic but poroelastic, and if you want to consider that there are no bubbles but just vessels, so they are connected inclusions. So this complicates very much the problem. This was the simplest probably setup. So maybe you have to relax the periodicity and also go to numerical homogenization or stochastic homogenization because even in this case the periodicity was nice, but it's very restrictive if you want to do real applications. So this is already the end. I want just to advertise one thing before I close. So there will be a workshop in VS about homogenization theory and application in October. Some of the speakers here are also speakers. Oh, Ralf Konuber will be there. Daniel Persson will be also there. So if you want to have more information, you can remember the short name. It's a short workshop. So it would, if you're interested, you can register. And let's also thank you for your attention. Just porosity, because yeah, because the mesh is. And where do you use microstructure information in your inversion? So I used to generate the data. Yeah, I used the data are microscale and the.
But if homogenization doesn't hold, then this approach, then I mean you cannot really invert for homogenized.
So now. Yeah, sure. Yeah. So the thing, so I don't use for inverting the inversion is only based on the effective. So it doesn't know anything about the microscale, the microstructure. So the
underlying assumption that the microstructure information can be used to invert homogenized function. There is a homogenization has to hold.
Yeah. So you need the problem is derived with a periodic thing. All these assumptions have to hold. But in the example, so the inverse problem doesn't know anything about the microstructure, yeah. But okay, the good thing is synthetic, so the data are generated in a similar setting, so it's not real data. Yeah. 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 Yeah, we try. Yeah. We try also. Yeah, we try also to generate to fix the process and generate the microscale, not periodic. Yeah, so this stochastic is, and it doesn't work very good. If you allow, for example, just to change the shape a little bit, then it's fine. But if you try to make elliptic, they are also changing the direction, and it gets worse and worse. Yeah, it's very.